Well, I was here a few years ago giving a talk entitled Rethinking Time in Distributed Systems. And that talk was really all about laying the groundwork for doubt, that the way that we look at time in computer science is a oversimplification. And when we discuss the difference between physicists and computer scientists, I said that both physicists and computer scientists don't understand time, but at least physicists will admit it. What this talk is about is to go quite a bit deeper and actually do the best I can in a lecture of this time, a short introduction to some of the key problems that arise when you start thinking deeply about time, and then try to relate them to what we do in designing our software and architecting our infrastructures. And I hope to just sow at least a seed of doubt in the minds of computer scientists that their existing concept of time needs to be re-examined. So that's my goal for today. I begin with a computer science quote, which I actually love. It's from a book by Andrew Hodges, which talks about Alan Turing, and it's a very famous book amongst our friends here at Stanford. But he pointed out something very interesting, that Church's ideas and Turing's machines are rooted on this concept of doing one thing at a time. But we really don't know what doing is, and we really don't know what time is, until we dive deeper into the mysteries of quantum mechanics and start to understand what we really are getting at the macroscopic measurement of these observations that seem to confound us when we try to think logically about them. So what I'm going to do today in the time allotted is to try to give you an idea that will make you walk away and think and say, I want to learn more about that. And then hopefully you'll follow up some of the references that I've given in the end of the paper, and also the end of the presentation. The last page has a bunch of references on. And we might be able to continue the dialogue, and the computer science faculties around the universities around the world, to say maybe there is an elephant under the table here that we should be paying attention to. So first of all, I want to point out something. This work is based on the work of many other people, and in particular, I'm not claiming credit for most of what this is. The core ideas go back to Stuckelberg and to Richard Feynman, who actually laid the foundation of what I'm about to tell you today. The talk is going to be in three parts. But before I say that, the key people that I've actually talked to some of these issues about, who have generously shared their time and answered my questions, very often for several hours in their offices in their institutions. And I'm deeply indebted to the questions that they have asked me, and I'm absolutely certain that they will probably disagree with a lot of what I say, and it would be a very lively conversation, as it always is, because each of these experts actually argue amongst themselves a lot more than they argue with me at the moment. I have also targeted this talk to this audience. So if we have computer scientists and electrical engineers and physicists in the room, I hope not to offend the physicists. I hope not to offend the computer scientists, but I hope to, get right to the core of the electrical engineers guys, because you're the ones that's to blame for some of these things, because you should know better. You've done Maxwell's equations after all. So the motivation for me is what I'm doing in my life is I'm making computer infrastructures more reliable and more secure and more agile. Those are the very carefully chosen words that I use with the people I'm working with. And you'll notice that the word security is in there, smack dab in the middle, and it fundamentally is something that we need to do something about security. For example, we think about reliability, but perhaps we need to think about it deliberately in a different way, because things keep failing. I mean, all of these Dropbox outages, all the Google Mail outages, all the AWS outages, I mean, they just keep coming up. Every time I see these emails come up, I just store them in like a log of all these things happening. And it's now getting to be hundreds of thousands of reports that these things are offline for periods of time. So it's an interesting question about reliability. And I use that word instead of availability because they tend to do some spin doctoring around the word availability. Can we talk about security differently? Security is absolutely the heart of what I've been working on for probably now 6 years. And it was because 6 years ago, actually 7 years ago, I had an incident working on a government contract out of my house with several other engineers, and I ended up with all my machines being polluted, and I couldn't figure why. And the last thing I wanted to do was to become a security expert. Unfortunately, it didn't help me. I got swamped with, and I had a friend who was the director of network security at Lawrence Livermore Labs, who came to my house and he put a packet sniffer on my wires, and he said, "This is not an ordinary attack. You're under a professional attack." I went, "Oh my God, what's that? I've never heard of it before." And he said, I said, "What should I do about it?" He said, "First turn on your networks." He said, "Then dump all your PCs, buy some Macs, and you might buy yourself some time." So I bought a Macintosh that day, and I actually had it up and running with my QuickBooks accounts on it. I think it took me like 45 minutes, and I was blown away because I spent weeks and months trying to get all these viruses off these machines. That was my wake-up moment for security, and ever since then I've been thinking paranoid thoughts about it. So you know where I'm going on this. Security isn't just about encryption and key management, it's also about presence management. How do we do heartbeats? Why do we do heartbeats the way that we do? And why aren't the heartbeats themselves in a protocol which guarantees that they can't be snooped? And this is actually not a hard problem. I know of several people who claim to have an algorithm that can solve that, and there are several products that you can buy from companies that claim to do it. It's just that they're not used in OpenSSL. Which goes on to say, well, should we use timestamps differently? Wall Street wants to do high-frequency trading, and there's lots of discussion about using timestamps for various reasons that, as I'll go into later on today, that won't work, at least not the way they think it will. Can we do transactions in a different way? And I hope to be able to sow seeds of doubt here that the common way of doing two-phase commit, for example, in a database, up in the application layer, using this theory called serializability, is actually not a good way to do it, because first of all, it's an extremely low performance way of doing things, and secondly, it also has a much higher likelihood of failing for various reasons because of all the extra code it has to go through. We'll talk about that later. And then the big one here is concurrency. I heard a very famous computer scientist from UC Berkeley talk about SDN recently. I won't mention his name. You can find him on YouTube. Look for UC Berkeley. He also did a great talk at Ericsson too, with a lot of similar material. And he said, there's probably about 10 people in the world who understand concurrency or distributed systems. And I was thinking, what a thing for a computer science professor to say. I'm thinking, wow, doesn't that just be a big red flag that there's something wrong with the discipline of computer science if we don't know how to teach distributed systems and only 10 people in the world know how to do it? And I have myself experienced lots of people working for me in my prior lives who've done lots of distributed systems, and I think the thing that is missing is that those 10 don't even know. And I want to try and convince you, at least a little bit today, that one of the reasons might be that their underlying assumptions of what they're doing is based on a flawed understanding of time. And if that's true, and I think it is, then we might be able to do far better than we're doing right now in building concurrent systems. By the way, the reason why even the very best can't understand distributed systems is because as soon as you get beyond a certain scale, a certain size of number of machines, the cognitive complexity goes through the roof, and a single human brain can't hold it all in there. That's really the reason. But there are other reasons. Even if a single human brain could hold all the information that he was ever told and be able to compute it, thinking through his algorithms, he'd still find that we don't have a good foundation for the way that our infrastructures work when it comes to time. So I'm going to begin with, I'm going to give you 3 parts to this presentation. Part 1 is basically the physics, and I hope to be able to talk to an audience who's at least heard of special relativity and general relativity before, and may have a passing, acquaintance with quantum mechanics. I can't, in this time available, go deep, unfortunately, I will be very happy to point you to the great places on the web where you can get really good educational material on these. In particular, Stanford has an awesome set of lectures that Lenny Susskind did on general relativity, on special relativity, and also quantum mechanics, which he's very famous for. And I thoroughly commend them to you if you want to learn this stuff. Do beware, if you are Leonard Susskind is how it's spelled. I do beware, physicists and mathematicians and engineers and computer scientists all speak different languages. So their conventions and their mathematical symbols and the way they draw space-time diagrams is all different. So the language barrier is kind of like first understand the different symbology and then understand the different diagrams, and then you can really understand it much easier after that. So I'm going to begin right now with this, this term, the skyhook. A lot of us in England, I don't know if this happens in the United States too, you know, we're apprentices, you know, helping our fathers and, you know, getting a spare job on the side, you know, outside of school, on building sites, for example. And the site manager would typically, when you first came on the site, would tell you all the rules about safety and so on. And then he would send you off to the tool shed and say, go and get me the skyhook. And so the usual thing was you go wandering off to the shed and you search for it and search for it and search for it. And after about half an hour, you come back and say, I can't find the skyhook. And of course, everyone will start laughing around you because there was no such thing. You know, it's like you shouldn't, you know, it's a joke. It's like, you know, all the jokes we have in the Merchant Navy when you go across the equator. It's just one of those things that English people make fun of each other about. And, you know, kids in their mid-teens are ideal for having that experience. But this skyhook thing really kind of interested me. I'm thinking, well, how could I have a skyhook? What could I put in the sky? Can I write in the sky? Can I? And now, of course, there are things called skyhooks, and they're usually on a helicopter, and they drop a hook, you know, but that's not really a skyhook. That's a helicopter hook, right? And I want you to keep in mind this notion of a skyhook that is an illusion. It's something that doesn't exist. You can't hang something on a background, whether it's in space or whether it's on the Earth. You can't hang something on something that's not there. And that is the essence of the problem in time and the way that it's typically misunderstood in computer science. So we'll begin by saying, well, what do we know as time? Well, the first thing I want to debunk is this idea that this time that we think we're looking at in our cell phones and our, you know, watches and so on, even though it's all tied together through, you know, some network or wireless system, actually has an interesting problem. The way that UTC, the Universal Coordinated Time, is defined is you know, hours and days and minutes. But the problem is the number of seconds in a minute can be either 59 or it can be 61. And every so often it will add one or take one away. It turns out that it almost always adds one. In fact, it has added one all the time since, but because of the tidal forces in the Earth is slowing down. So what we're really doing is we're trying to get this notion that the Earth is spinning around at a constant rate. And that's what we used to use for time for the longest time until we discovered Cesium clocks. And then we said, oh, but the Earth isn't spinning around at a constant time. It's actually sometimes a bit slower and sometimes a bit faster. And it's like it varies a little bit. And it's fairly random. It's odd that you can't predict it. So what happens is there is this office in the United States, and there's another one in each country, which basically says, we're going to give you a warning 8 weeks ahead of time that we're going to give you a leap second. And that's what they do. And so if you've got these, you know, these batches of information coming to you, you can, you know, use these tables to decide what kind of when you're going to do these leap second changes in your timing infrastructure. So therefore, UTC is discontinuous. You can't expect it to be monotonic and smooth. And of course, we're all experienced with this when we deal with, you know, leap days and leap years. And we had the problem when, you know, we had the millennium problem when we go over the year 2000, we all thought all our computers were going to crash. And so it turns out that time is a very problematic concept that's very, not very technically clean, let's say, in the way it was put together. And the reason for that is it's not technically clean in the physics itself. So in other words, this isn't just, you know, a bunch of human beings trying to define what time is. You know, I'm trying to make it as close as possible to the rate that the Earth goes around. It's beyond that. When you go into the physics, which we will, you'll start to see that there is no thing that you can put your hook on. There's no time there that you can say, that's it, that's real time, or that's the thing that everyone can measure and we can give it to everyone. So what this time is, effectively, is like a committee. It's like all these 200 different clocks around the world from 50 different countries, all actually do a weighted average. And that's like it's like an election for what, on a continuous basis of what is time. And that's kind of what we receive through GPS and through our network time protocols and everything else. Do you have a question?
Noticing the relationship between cesium clocks and hydrogen masers, they can't even get continuity with just one. They need the pair together in order to get the idea of continuous time.
So that's a very good point. You use the masers as well as the cesium clocks, and you need two of them to get continuous time. I'm going to go deeper into that quite a bit in the presentation. But I'm trying to lay the foundation of doubt here. It's like, this idea that we can say that the time is a kind of like a committee-agreed thing, which country has the most weight and which one is the biggest expert, and it's an internationally agreed thing that's constantly being changed and moved every 8 weeks when we decide to have leap seconds. Now, 50,000 years from now, the day is going to be, like a minute longer than it is now, because the tidal forces in the world, actually not a minute, I apologize, I think it's a second, because the tidal forces are slowing things down. So as time goes on, the Earth's rotation is getting slower. And what we're trying to do is emulate some ideal of that when the underlying reality is not ideal. Eugene?
You're trying to say that time is a convention, which is actually in a very nice book published by the National Bureau of Standards. The problem, unfortunately, with a lot of computing, a lot of other fields, is we're trying to do absolute time. And the reality is, a year is not 365 days, and that's why we have leap days as well as leap seconds and years, and there's a lot of this detail. Two good diagrams to look at are the wobble of the South Pole that was done in the late 50s by Paul Seipel. The South Pole is not, or I should say, the axis of the Earth is not this nice clean line. It wanders all over the place by about 10 feet. And similarly, there's a 60,000 year wobble as well too. All of these factors add up to.
So I'm going to suggest that the longer discussions perhaps at the end. If you have any clarifying questions because you didn't understand me, certainly ask. But I've got room at the end of the presentation for a discussion. Now I'm starting you off slowly here, of course, sowing these seeds of doubt of time. So then let's take a look at what happens with relativity. Now, many of you have already done kind of like a quick relativity course in school or whatever else. I tend to find that most physicists usually have a visceral understanding of relativity, at least certainly special relativity, and if they've done a general relativity course of that too. But very often people who do it from another discipline, from EE or from computer science, tend to have had just enough lectures to say how they can calculate the Lorentz boost, for example, and and say what would happen if a spaceship took off at 0.8 of the speed of light and how long it would take and so on, and then they move on to the next subject. That very often does not give a good visceral understanding about what time is. And there's a very good paper, it's in the references, that actually did the testing of students on different disciplines to find out how well they understood relativity at the end of the lectures. And it came out very clearly that this knowing the formulas doesn't give you an understanding. That's the problem. So really what happened with special relativity is, you know the Einstein description, basically says I've got a moving train and I'm bouncing photons backwards and forwards. He calls it a light mirror. And what happens is there's a person on the train who's measuring, the time of traversal of these light pulses, and then there's someone alongside the track who's stationary, and each of those observers gets a different result. And that was the paradox at the time, the complete utter paradox. Why did they get a different result when they measure both time? And then if you use time and the distance and measure distance of the railway track, you get another odd thing. It seems like the length of the train is shorter from the stationary observer, but also the length of on the track, the stationary appears shorter to the observer on the train too. And so Einstein scratched his head about this and came up with a special relativity. I'm not going to go through the details. The point is this. It's based on the fact that the speed of light is a constant. No matter what happens in the universe, everywhere you look, the speed of light is always the same. And no matter how fast you go, the speed of light is always the same. So if you're going, 0.8 of the speed of light and you then meeting someone else head on who's going at 0.8 of the speed of light, you can't add the velocities. It's not 1.6 the speed of light, it's just the speed of light. And that is the essence of special relativity. But I want to say one more thing. The big thing that Einstein discovered, and what we're going to go through in detail here today, is this notion of the relativity of simultaneity. And really what it means is there is no privileged frame. There's no stationary frame. There is no fixed background. No Newtonian time, for example, or Newtonian space. This relativity of simultaneity is absolutely at the heart of the whole issue with time. And if we can get that concept over, then I think we can start to build on that as to what other issues there might be with time. So let's take a look at that quickly. We get, from Maxwell's equations, we get a prediction for what the speed of light should be. I put this equation in for the electrical engineers. I'm sure they will enjoy it. But then, of course, what Einstein added was something called the Lorentz boost, which is basically it's a factor that by which you have to multiply it in order to be able to compare times, to compare lengths, to compare masses, and so on and so forth. And what happens is you get pull out this function, we call it gamma, which is the Lorentz boost, and that often is used. That symbol is often used in the formulas everywhere when you're trying to calculate things. And it does this kind of thing. It moves it looks like there's not much going on at, the low velocities. But when you get closer to the speed of light, this thing starts to climb like a homesick angel. And it goes on forever. It's an exponential. And you can never actually get to the speed of light. And that's the reason why people say nothing can go faster than the speed of light. Because as mass increases, you need more energy to push it. But there's a point in the mathematics where if you've got a singularity at the speed of light, then you need an infinite amount of energy, and that's more energy than there is in the universe to actually get you past the speed of light. So that's one of the reasons why nothing can go faster than the speed of light. And the speed of light is experienced by any massless particle. For example, the photon is a boson, it's massless, and it moves at the speed of light. What does that mean? Well, we have these things called light cones. Whoops, didn't want that one. Let's try this. There we go. So, all right, so we've got our idea that there's this speed of light's a maximum. And if you look at, there's basically, there's time going up, and space is in this direction. We're showing only 2 dimensions of space here. So ignore the third for the moment, but it applies it directly. So what we're looking at here is everything that's in the light cone basically is possible to influence that point in the middle that we've got to focus here. And if that thing in the middle wants to influence anything, it can only influence those things in its future light cone. This comes straight out of something called Minkowski space, which is adding x, y, and z and time as a 4-dimensional mathematical space. And I'm going to tear this apart in a moment, so this is a good point to really listen carefully. This plane that we put in the middle, this thing they call a hypersurface, that's our attempts as human beings to introduce simultaneity. Einstein already proved that simultaneity was relative, but we kind of pretend in an ideal environment, an environment that we call an inertial environment, that we can play these games and have these simultaneity surfaces. And that is where the biggest issues come in designing our systems, designing network time, for example, high-speed trading, and all of these things. They're all attempts to try to recreate that simultaneity surface. And there's a bunch of issues because it's an illusion. It doesn't exist, except in our minds. However, the mathematics of Minkowski space, when it's applied to the problems correctly, gives you a very good result, very close to, in fact, impeccably close to what you would find in the measurement. So the theory of relativity has absolutely been proven. What I'm going to do today is I'm going to say two things. First of all, this manifold here, which has got stuff going on inside of it, the only thing that's really going on is across the path between two things that are interacting. The rest of the manifold doesn't carry time. It's just like the sky can't carry the hook. And our attempts to create this hypersurface are the root of all of our misunderstandings. Now, what I'm going to do now is I'm going to put 3 different reference frames on here. A different reference frame is nothing but another entity. It could be a vehicle, an airplane, a spaceship, moving at a constant velocity. Remember that, constant velocity. And there's 3 of them on this one. I've got the red one, I've got the green one, I've got the blue one. Now, what happens here is the event along the green line there, you can see clearly that B happens before A on this line because, the x direction is positive to the right. But you'll notice that because there's a shifted axis here and the movement of this other inertial frame that's moving by it, that B happens before the blue line and it happens after the red line. So in other words, the ordering of events that's experienced is different for these 3 different observers. And let's go back to the railway car that we started this experiment on. What we were doing, we were bouncing photons backwards and forwards. What Einstein was doing in 1905 was really creating clocks. The whole of special relativity is nothing but the construction of clocks. A lot of people think it's the construction of an abstract form of time, and it really isn't. It's about clocks. What makes a clock work? That is the enigma, is like, what is a clock? And then we'll talk about that more later. So the first thing I want to suggest to you is that photon clocks are an interesting way to start thinking. How do we use photons bouncing between things to create clocks? I mean, part of the point that you were making before. And it turns out to be interesting because, a single photon doesn't experience time, no matter how far it travels. So I would put to you, the reference at the bottom of here, you can see after the presentation, there was a very, very extensive argument for a long period of time. And in fact, Einstein was involved in this argument. And he ended up being clumsy in his words. And then he made a statement and then retracted the statement. And this came from the analysis of that by Rickenbach. So Rickenbach basically discovered that every time we tried to do the following, is identify what the time was somewhere else, as opposed to what the time was here. Every time we try to do that, we get into a circular argument. We're faced with a circular argument because to determine the simultaneity of distant events, we need to know the velocity. And to measure the velocity, we need knowledge of the simultaneity of distant events. This is a very, very well argued and analyzed problem. And the bottom line is, oh dear, we're not going to have much of a chance here to put a skyhook on that thing because it doesn't exist. It's a circular argument. In fact, there have been some magnificent papers over the last 10 or 15 years, particularly by Julian Barber, who's gone through 5 different disciplines, from mechanics to thermodynamics to quantum mechanics, and in every one of them he's basically ripped out all of the presumptions that we all commonly make about time and discovered every one of them is circular. It's quite an eye-opener when he does that. So not only is simultaneity a myth, keep that in mind, because what we're going to do in computer science is try to recreate simultaneity if we can, because we're going to pretend it still exists. Because it does in our imagination, of course, right? But there's something else that's also a problem. Even in this ideal world where you think you can do the mathematics and saying, well, if I got an inertial flame, I can calculate it's going at this velocity, and I use the Lorentz boost, and I can calculate what the time should be for him, and then I, know the distance, and I can pretend I know I'm experiencing time the way they are, whether they're a minute ahead or an hour ahead, or depending, or much further ahead, depending upon how fast they're going. But this is the bigger problem. Inertial frames themselves are a myth. An inertial frame basically is what happens under Newton's laws. It's, something continues moving unless acted on by a force. Classic Newton. The problem is in relativity is if you have any accelerations whatsoever, it blows that out of the water. Because accelerations belong in general relativity, not in special relativity. And there's an entirely different framework for thinking about that. So the easy way to think about this problem is, have you ever tried playing ball on a merry-go-round? Yeah. You know how hard it is? Well, actually, light does exactly the same thing. You point it in a direction, and if you're on a merry-go-round, the Earth, then what happens is it does strange things too. And you end up not being able to get a handle on where you should throw things and how you should point things because we're on a rotating object. So there's not only Coriolis accelerations going on, there's all sorts of regular, accelerations going on. And then on top of that, we've got gravity, which basically nails this coffin shut of the idea we can never have an absolute notion of time.
We have this twisting of space-time as gravity probe B attempted to measure, which apparently the difference in the angular momentum of the universe versus the Earth causes distortion in the space-time because there's a disagreement between the two.
I have read a lot about that, but I don't want to make any definitive statements in the answer to your question. And that's because I'm aware of some controversy there and many different dimensions. But the point you made is actually a very good one. I am now going to go, however, on to general relativity. Now, you don't have to worry. I'm not going to give you a course on tensor algebra. These equations basically say something very simple. And you can actually get to know how this whole equation works in about 3 different lectures by Lanier Suskind online on Stanford Online. And great set of lectures, fantastic. But what it means really is that the left-hand side is the gravitational field, which is the curvature of space-time. And the right-hand side is the energy density. Now notice I didn't say mass, and that's because physicists think that energy, mass, frequency, they're all the same thing to a physicist. But what that really means is this. Matter tells space how to curve. In other words, it bends space. Whenever the sun or a planet is in space, it's going to warp the space-time around it. And space-time tells matter how to move. So anything like photons, passing by Mercury are going to be affected by that gravity, and they're going to bend. And that's exactly how we verified general relativity. But as far as our discussion here is concerned, what we need to know is, what does general relativity tell us? It tells us that space-time itself is a dynamic manifold. It isn't just a flat surface that we can pretend to do things on. So this is even worse than the Salmon-Inertis surfaces don't exist. Secondly, that acceleration and gravity are equivalent. If you remember any of the popular stuff on general relativity, you can't, if you're in an elevator and you're being pushed up by a rocket at the force of g, you cannot tell the difference. Then you basically in free fall. If you're on the surface of the Earth, it's stood still, you're feeling the force of g. Or if you're in a rocket in space and you've got a rocket that's propelling you at the force of g, it is called the equivalence principle, and you absolutely, in principle, can't even tell the difference on these things. Now, that's the way it's described. Sorry?
I don't understand that. I mean, it may be true at a point. It can't be true in any region because the Earth's gravity has a gradient and you can measure it over a space of a meter, say. So
that is absolutely correct. In fact, if you have an elevator that's a certain height, in theory, if you've got sensitive enough instruments, you can actually measure what's called the tidal forces, and you do have a gradient of the gravity, and that can be measured absolutely. So thank you for pointing that out. So that's what we've got. There's another interesting thing that comes out of general relativity, and this is what where all the fun comes when you read the books by Stephen Hawking and Roger Penrose and all those people who enjoy writing the books for the public now. Time stops inside a black hole. What also happens, though, is there's this notion of background independence. So this kind of starting to lead us in a different direction. Background independence says, we acknowledge that there's no skyhook or place we can hang paint our numbers or assign something up there. And it's typically, general relativity is described as having no background, whereas quantum mechanics does have a background. It has a regular time-space background that all the calculations are usually done on. So let's talk about quantum mechanics. A little bit shift here. If we were to do a two-slit experiment, what this formula basically says is that we have a number that we can see, a measurement we can make, which on this equation, and we can say, let's look at light or some other quantum particle going through a double slit. So the question is, what is the intensity going through one slit, and what is the intensity going through the other slit, and then you divide them by the square root of 2, which is a normalization constant, just to make sure that the total probabilities equal 1. Now here's the key issue here. These kets, they basically are saying that you've got a complex vector. So in other words, the imaginary number I is in there somewhere, playing games. And when you start multiplying things around and squaring them, you end up getting strange things happen with the matrix that you work on. But also, that probability in slit A is a probability. It's like, what's the probability of you driving home safely this evening? What's the probability of you dying in an airplane crash? And insurance companies are interested in these kind of things. These are probabilities. In fact, a lot of people have said there's very little distinction between quantum theory and probability theory. It has been said that if you teach a student a thorough course of probability theory, then within a 2-hour course after that, you can tell them everything they need to know about quantum mechanics. And if you try to do it the other way around, you try and teach people all the odd things about quantum mechanics and all the weird things that can't be understood, they get confused, and sometimes they get, don't want to do that subject anymore the rest of their lives, and they get math phobia, and they don't want to do it. But if you teach them probability first, it doesn't seem so strange when they do quantum mechanics. So keep that in mind. All of quantum mechanics and all of information theory, for that matter, is basically about asking yes/no questions. In other words, you're expecting a binary answer. Did it happen or didn't it? So we're going to do a binary question here. So that thing at the top is the sum of two probabilities. So if we were doing quantum entanglement, which is, let's take an emitter that's capable of, emitting 2 photons at the same time, and there's various materials that will do this. They're parametric down conversion crystals. And what happens is there's a certain number of photons that come out that are always in pairs. And that they're entangled by definition because they came out of the same source at the same time. Now, when you start looking at what happens on either end of these things, you will still end up with this. I'm going to show you it here. This equation here, this blue line on is really the thing that we've got going on the left-hand side here, because there's 2 kinds of time going on here. Entirely different kinds. We call them evolutions. There's this thing called unitary evolution, which is reversible, and it's also lossless, and it's linear. It's linear in the sense that you can add the 2 things together. So in other words, you're going to get a probability of this happening, a binary variable, or this happening. But the probability of each happening is given by the coefficients on the front of these equations. Very simple. It's not difficult to understand this. But what is very difficult to understand is what happens next. What happens next is this second form of evolution, which is called non-unitary evolution, which effectively is irreversible. And it's dissipative. It means the energy and the information functions change. They've been entangled with the environment or decohered into the environment. And now all of a sudden you get either it's the top one or it's the bottom one, and neither. Whereas this thing is constantly evolving all the time according to some equation, typically the Schrödinger equation. But this event here, this non-unitary event, what Niels Bohr used to call the collapse of the wave function, is where all the fun starts. This is where we get into deep philosophical questions about what the meaning is behind this, because this no one can predict which way it's going to go, one way or the other. And the very fact that we can't predict it is what makes quantum mechanics so incredibly difficult to understand, because it's nothing like Newtonian mechanics, and it behaves very differently. I'm going to talk a bit more about these issues in a moment. So that effect, that change, is random, and instead of the Bohr's collapse of the wave function, in the modern term for this now, which is a more progressive thing as it's being entangled with the environment and as well as the apparatus, is typically called decoherence theory. But again, that's the process by which things become irreversible. So when we get up to the macroscopic world that we're in, we see everything as irreversible. I mean, time it's got a past, and it's got a future, and it's got this feeling that we're in the present. And that's, unfortunately, a prejudice that we have because of the way that we've been evolved as human beings to survive well on the planet. It turns out that other species have different views of time, and it turns out that even other societies have languages, for example, that don't have any tense in it at all. For example, the Hopi Indians had an entire language that didn't have this before and after words in it. And the same is true for some other societies that were investigated, and how differently it caused them to think. But if you really want a good description of this problem and how to understand it, or you'll never really understand it, but what you will do is you get a grasp of it so you know how to say it will do things. There is an experiment. Let's imagine I've just got one of these things here. I've got a thing spitting out entangled photons on both sides and a detector on both sides. And what happens is, if I send that particle out, then what's going to happen, I'm going to move time forwards now, all going up the page. So what happens is, I end up with, say, at the position n, for example, if I emit the particles, then I've got a light cone. And the question is, does that light cone overlap with the light cone on the things on the other side? So if I later up in the system here, if I've got photons being emitted, and there's not enough time for the light to get to the detector, then we're saying that's, it can't violate the speed of light, right? But what we discover is that if we put connectors on each of those instruments, and even though the apparatus is wider than the travel time of the speed of light, we do a coincidence measurement, which is typically you count the pulses and the times when they arrive. When you look in the time average record afterwards, you find that you get coincidences that make no sense whatsoever, that would appear to violate the speed of light. So we already know there's something very strange going on down here, especially with time, that we can't really understand. But what we do find is that the mathematics tells us exactly what happens. There's been a long-time long-time disagreement in physics about, well, what's really going on. And what you often find when you're speaking to a professional physicist is that they say, oh, that's all philosophy, I don't worry about that. I just use the equations, calculate the result, and when I go to my experiment, I get exactly that result. So that's all I need to know. By the way, this philosophy is called shut up and calculate. You have a question?
Bell's last paper on the mysterious pilot wave and the conjectures, which is to say the debate is still raging?
Well, it's absolutely still raging. In fact, it gets better every year. What he's referring to is this whole apparatus, by the way, is developed on something called Bell's inequalities. What John Bell did before he died is he figured out that this argument between Niels Bohr, who said that everything was complementary, it was a duality between waves and particles, and we shouldn't pay any attention to what we can't measure. So just measure it and don't worry about what's going on behind it, because we can never know. Einstein, on the other hand, was very much a proponent of there must be something real going on underneath. There has to be a real thing that we just can't understand. And he preferred a description called hidden variables, that in other words, something must be going along with this thing to give this effect. Now, I'm going to describe later on a different way of looking at this, the way I think about it, to help you realize that there's potentially some interesting things that you can think about too. So keep in mind this this paradox of Bell's inequalities, and these experiments, by the way, have been done many times right now by Elaine Aspect and by Anton Zeilinger, who's done a whole series of them. So let's switch subjects quickly because I want to stay on time here. The next problem is almost all physicists will actually agree that what we experience as time is actually the second law of thermodynamics. And this was described by Boltzmann very simply as the arrow of time comes from the tendency of nature to evolve into an ever greater disorder. Now, let's back up a second here. All of those equations that we learned in school, those Newton's equations, even the equations in quantum mechanics, they're all reversible. If you replace t with minus t, you get good answers. So they're symmetric with respect to time inversion. And that basically says all of our known laws are time symmetric. There are some strange things going on with kaons, but I don't intend to go into the details of that today. But in general, every one of our equations is time reversible. The only one that isn't is the second law of thermodynamics. And that isn't even a real law. It's a statistical law. In other words, we really do have a possibility of this entropy going up or down, and it's confused everyone for a long time. But the nub of the problem here, for those who like to think about it, is that when you get past the popular books on telling you that entropy is the arrow of time, you suddenly realize that there's nothing in the physics under it that tells you which direction of time entropy goes up. It basically says it should go up in both directions of time. So we only arbitrarily label time as going forwards and backwards in our heads, or in our graphs, or in our equations, or in our Feynman diagrams. And it turns out that it's not that straightforward. The backwards and forwards versions of time could easily be flipped and call the x and y, or call the p and q, or call the left and right. They're arbitrary labels that we give them as human beings. Both of these directions for time, entropy should increase. That's the puzzle. This is where irreversibility comes from, and most of this will eventually be developed from decoherence theory, and that's where a lot of the work goes on these days to try to describe this. But I'm going to describe something probably in the next slide is a bit better than this one. Before I do that, I'm going to describe information. So information and entropy have a very close relationship, and I'm going to describe later on about how they complement each other. There are a lot of arguments. It's a controversial subject, but entropy, from a thermodynamic perspective, seems to have the identical mathematical formalism as entropy from an information perspective, from Claude Shannon's work on the mathematical theory of information. And there are some theoretical arguments made that not everyone agrees with, that they are theoretically different. But in practice, they are the same. So in other words, the bits that we're measuring in information and the bits that we're measuring in thermodynamic entropy are exactly the same concept. There's something very important going on here that's similar. And I'll talk more about that in a minute. So this is a paper that was published in 2008 called The Arrow of Time Dilemma. And this is by Lorenzo Marconi, who resides in Italy, and he's been at University College London, and I've corresponded with him fairly heavily on this. He basically wrote a paper that was directly aligned with my instincts about how this worked. And he articulated it beautifully, and then he goes to say at the end that this is just a tautology, and so because it's a tautology, we can never measure it, so therefore it's not worth thinking about. It's not going to affect the real world. And then I pointed out to him that there are ways where it can affect the real world, even when the evidence goes backwards. So let's follow this argument carefully. The laws of physics are invariant for time inversion. The phenomena that we see in everyday life don't go backwards in time, they go forwards. This is a classic, layman's description of, you put your cream in your coffee and it doesn't swirl itself out again by itself. Within a quantum mechanical framework, all the phenomena which leave a trail of information and hence can be studied by physics, are those where entropy necessarily increases or remains constant. There are situations where it can remain constant, particularly when you're dealing with reversible or Landauer systems. And then he goes on to say, the phenomena where entropy decreases must not leave any information of their having happened. And he then says, this situation is completely indistinguishable from their not having happened at all. So what's going on here? So if I have an object here, and I hand it to you, okay, and you're kind of, looking around the room, not paying attention to it much, and then she hands it back to me, I can then say, did that happen? If you weren't looking, did it happen? We used to laugh at the naive joke about, if a tree falls in the wood. Well, there's a very deep philosophical problem in quantum mechanics about exactly that issue. And if you're not looking, it doesn't happen. This is what Einstein used to call, the problem with the moon. Is the moon not there when I don't look at it? This is an extension of the Schrödinger cat argument and so on. So there is a very deep issue in if there's an identical situation before and after you looking at this event, then did time go forwards? And we're going to talk about that in more detail later. So this is the issue. The second law of thermodynamics is reduced to a tautology. If you can't measure it because evidence was erased, then what's the point of even thinking about it? It turns out that if I, for example, passed you that object again, and you had an object in your hand that was identical, I would be preventing you giving that object to her because she's already got her, orbital shells full or whatever else of the object. So the point is, I am affecting something that could have leave a trail. And so it turns out, and a lot of this, it comes down to the Pauli exclusion principle in the 0 point energy in the space. But you can have a perfectly reversible process that while it was in one of its states, did stop something else happening that could have happened, that then leaves this like ghost of a trail behind it. This is what we think is going on with the Bell state measurements. So let's talk now, we've gone through the physics. We've said, okay, special relativity gives us a major problem. There are no inertial frames. Simultaneity is a myth. General relativity really nails the coffin shut by saying, we've got time is in a very different thing, whether it's in an intense gravitational field or less intense gravitational field. We can put atomic clocks at the bottom of a building, at the top of a building, and they will measure different times in our gravitational gradient that was in the question earlier.
So I'm a little confused because you seem to be saying at the beginning of your talk that time is just a convention, it doesn't actually exist. And now you're saying time is this thing? I'm a little confused.
I've gone through a number of points, and you're absolutely correct. In special relativity, and to some extent in general relativity, the way that we think about time is just a convention. We invented it in our heads. In fact, we even standardized it with the NIST as to what we think time should be. The problem is we've imbued that unconsciously into our way of thinking, such that we can't think outside that box when we start programming our computers and we start thinking about the nature of concurrency in large distributed systems. That's my point. I hope to be able to answer you better with more slides further down, if you'll permit me. Thank you. All right, so kind of tongue-in-cheek here. Mark Twain has a very wonderful saying, which I'm very fond of, and in order to be able to learn something new, we often have to unlearn something old. And so it ain't what you know that gets you into trouble, it's what you know for certain that just ain't so. So that's my message to people who think that time is just, Newton's time. No, it's not. It's a very much richer and more interesting subject than almost anything else in mathematics or physics or computer science. It's the central issue. And since computer science depends so much on time for its underlying assumptions, I think that the computer science departments in all universities should be paying a lot more attention to it. So let me go here to the two things that I think are the biggest issues. There's an assumption that time is continuous. That we start off on one side and there's this line, you know, the real line as we call it, which points in this direction, and it goes on for infinity in the future and comes from infinity in the past. And that whole idea of time is a continuum. We basically think time is continuous and we can keep on dividing it down into smaller and smaller parts, and we have this issue with events versus intervals. Eugene?
The problem is computer science departments teach the Turing tape.
Yes.
It's a one-dimensional linear thing. And that actually comes from real analysis when they teach, the reason why they teach calculus the way they do is you have deltas and epsilons that you derive, and it's really an extension again of linear algebra.
You're absolutely correct. And Turing machine is where computer scientists typically get their idea of time. But 2 slides. Go ahead.
Something called Planck time. Don't
Yes.
they already have the notion that there's a shortest interval of time?
That's a very good point. You're absolutely correct. But this lecture is not about Planck time. I'm going to try and prove to you later on in the slides that we don't even have to go anywhere near Planck time in order to be able to get things that are completely out of order and unmanageable. And you'll probably connect the dots very quickly when I show you how I do that. But
Conjecture, it's not something which people have substantiated, right?
well, it's substantiated in the sense that all of our equations meet at the Planck scales. And there's a lot of physics and philosophical and cosmological questions about what happens down there. And the reason why it's interesting is because we have to think at that scale when we talk about the Big Bang. Because there comes a point, you know, early enough in the Big Bang where things are operating at the Planck scale. So that's how, when we can do the mathematics on it, that's how we were able to do, for example, the causal dynamic triangulations, which is one of the forms of quantum gravity that is used to measure this. It also has a lot to do with the way that string theory can be put together, and then we go back in time to see what would happen to it when we look at the singularity that was called the Big Bang. But I want to talk about computer science in this section. Physics is fun, but computer science is where I think our primary interest is. And I mentioned this thing called unitary evolution. It's reversible computing. It turns out that the biggest motive in the computer science departments and the electrical engineering departments is to say, well, we'll use this thing called Landau's principle, which basically says that energy is not dissipated unless you erase information. So if you convert a piece of information from 0 to 0, no energy was dissipated. If you overwrite it with another 0. If you convert it to a 1, energy is dissipated. If you convert it from a 1 to a 0, energy is dissipated. And it's basically, it's called Landau's principle. It was an extremely interesting discovery when it was made. And the people who do a lot of quantum computing look at this as a very serious theme. But the person who did most of the work to extend it is Charlie Bennett. So I'm picking an ACM conference here. It's described at the bottom, I think, so, or here on the side. This is the first ACM conference on reversible computing. And basically, you don't need to look at the whole slide. This is what's interesting. When Turing, Shannon, von Neumann, their contemporaries formalized the notions of information and computation, they missed out notions of reversibility and quantum superposition. In other words, they didn't even think of it when they developed their theories. So what is reversibility? It's really, this is the thermodynamics of computation. It's this thing about Landau's theorem I was telling you about. Superposition is absolutely the heart of quantum mechanics. It basically says I've got two variables, and either one can happen or the other can happen, but it's not like it flips in reality. When they're under the quantum hood and they haven't been measured, it's a strange mixture of the two, and you can't tell what they are. This is this fuzziness of quantum behavior. So something very, very strange is going on under the hood, but we can calculate it as probabilities. It's a statistical result. It's not a result like, you know, you'd get in Newtonian mechanics. If you had a baseball bat and you hit the ball, it'd give you an exact result. It doesn't. So this is interesting. And so the founding fathers essentially of our field of computer science and information theory. Go ahead. John Norton. I have, a long time ago.
He has a paper currently in prep that is a no-go result for Bennett's reversible computing?
I'd love to discuss that with you afterwards. There's a lot of evidence to support Charlie Bennett, but I have my personal questions, let's say, and so I'd love to delve into that later. It's about 5:15 right now, and I've got 15 minutes left, so let me go through this quickly. Reversible time is the secret to consistency. If you want to build a system that's consistent, for example, you're building a large infrastructure, multiple data centers, you're doing replication from one data center to another, you want to say, what happens if an airplane goes through my building? How do I carry on operating? What happens if I've got my networks failing and coughing and spluttering all the time? And then I have to get back to normal operation when this thing gets back again. All of these things depend upon us having an understanding of the consistency of our data. So it's not an easy problem. For example, you've all had the experiences of Google and of Apple and of Dropbox creating, losing all your data. Literally, there's a mode of operation in their algorithms where you just, all the data disappears. It's gone. I hope you don't ever hit into it, but I know exactly how to hit it on my systems. Or the other alternative is you get all these duplicates. All of a sudden now a poor human being has to go and sort out which duplicate's which. So the data synchronization algorithms actually have some very fundamental flaws in them that are right in the algorithms. And when you look carefully enough, the flaw is in this assumption that time doesn't go backwards. Because if you want to do a transaction, the whole notion of a transaction, for example, a two-phase commit, is like, okay, do you have $1 billion and you don't have any? I'm the transaction manager. And I say, are you ready to increment your bank account? And you to decrement your bank account? And you both come back and I say commit. And if either of them don't give me an acknowledgement, then we do a rollback. That rollback is a primitive form of reversible computing. So transactions need that atomicity in the relationships between the machines in order to be able to guarantee that something either got there or it didn't. And we don't do that very well at the moment. Now, it turns out that whole two-phase commit thing is related to how acid properties in the databases. And Google has done some very excellent work recently, and I commend it to you to look it up. It's called True Time. And instead of having this point on a line that's moving forward that we call present all the time, this single number, like a scalar incrementing, what they've done instead is they've put a bracket on the line. And they've managed the bracket. They said there's an early bracket and there's a late bracket. And everything before this bracket has not happened yet. And everything after this bracket has absolutely happened yet. And you have an API that the application can call to find out where this bracket is at the moment. Now, of course, what they're doing under the hood is they're actively managing these brackets. They're managing the delays on the network and calculating the round-trip delays and saying, should the bracket be really small because everything's nice and tight, or is the bracket really wide? What they can do is they can do effectively ACID properties or full transactions over a WAN. That's quite a hat trick. It's really good. Now, it turns out not to be theoretically correct, but it's a really good try. It's very much in the right direction. What you can do basically is you reduce this down to a certain minimum uncertainty that's a lot smaller than the uncertainties we get with more crude thinking about timestamps that we've done in the past. So it's definitely headed in the right direction, but it's another attempt to just try and create a simultaneity plane. We're trying to make everyone think the time is the same. The time is synchronous.
Synchronized across physically disparate regions.
Yes, they are. In fact, the way that Google does it is they take GPS time, they drop them into the data centers, they've got multiple atomic clocks in the data center which are then synchronized, and then those then provide time stamp brackets to the APIs.
Reversible time? I'm missing the argument.
The connection to that is that when we do reversible time in transactions, we do it through a two-phase commit and a rollback. The rollback is reversibility.
Yes, but Google's spanner isn't doing anything about reversing it.
Google span is not doing anything about the time. What they're doing is looking at what transactions are overlapping on the same objects so that you can block one or make one retry.
Well, let me clarify. Google is in fact using a rollback and a bracketing in order to enforce coherence in hindsight. So they're in fact using transactions within the bracket in order to get the effective coherent time.
That's a good way of describing it. Thank you. All right, I haven't got much time, so let me move on. Computer science problems. So we've got problems in computer science about this reversibility issue and also the continuum issue. But we also have, and I had a whole bunch of slides I was going to put in here, and I realized I wouldn't have time to talk about them. But I want to talk about two major areas where we do tend to have serious operational problems with time. One of them is with networks. And I spent some time with the large networking companies recently and had lots of nice arguments with them about how useful this new IEEE network time protocol was. IEEE 1588, I think, is the new number. And basically, it's a much more elegantly thought out, much more precise form of being able to minimize the accumulation of errors through a series of machines when you're trying to give an accurate timestamp to a machine. Now, there was an interesting piece of news this morning. I wonder if I've got it in the one right past this. No, it's a bit later on. About, can you use this for high frequency trading? Now remember, that's just a process of trying to make everyone think the time is the same. And this simultaneity plane that I'm talking about is an illusion. It doesn't exist. It's a fantasy in our minds. Now we can actually get statistically closer and closer to it, but we can never even get I'll give you an example. London Exchange, for example, talked about being able to give everyone accurate time if we give these, fiber optics to everyone all the way down on the London trading floors, and nothing else goes on those fiber optics except the time signal, then we can synchronize everyone to within 1 microsecond. And I'm thinking, 1 microsecond? Huh. What's that? That's what, a megahertz? What if... What are our computers running at right now? 3 gigahertz? I mean, there's like 3 orders of magnitude difference here in the amount of stuff that can go on under the hood and the time, this very crude, best thing they can do for time synchronization. So it's still a long, long, long way for you to be able to here's my point. If you want to be able to use timestamps, use them for auditing. Just use it like a checksum that you add on the end of your message or your database or whatever else to make sure that something's gotten done. You can go back and check it later. Because the interesting question is, where do you get your timestamp from? Did you get it from the cesium clock in London, from the National Physical Laboratory, or did you get it from Boulder, Colorado, or from NRL or someone else that's sending you a clock signal? So in other words, there's going to be this competition in the world for who's going to be the one that gives who's the one that says this is the real time. Pardon? The Bitcoin blockchain. That's right. It turns out that, this is in here anyway, we're going to talk about this in a moment. Now, virtual machines have a really interesting problem. You can turn off virtual machines literally on a cycle. And those virtual machines go to sleep and they have no idea. When you wake them up, they wake up on the very next cycle. They have no idea they've been asleep. They could have been asleep for a second, a minute, a year, 10 years, and then they wake up and they have no consciousness about, until they have an interaction with network time, for example, and they discover that the clock suddenly jumped. And, oh my God, so did the calendar, years. It's an interesting problem because that relates directly to what I'm going to tell you next about how this stuff can work. So very quickly, I'm going to say, if you want to architect something in a computer science system, you've got to get the observer right. Dealing with the identity and individuality is a big issue. The human observer might be the person on a web page. Multiple observers might be people on databases that are doing transactions. They all have to be consistent. And the background processing can have a very different view. What it means is if you have very different views about how you see time from the different processes that you can have in the system, and you don't have everything heavily using coarse locks, for example, then you can get very much more fine-tuned versions of insight from this. So part 3, the potential insight. This is where I'm starting from. Very profound. What is time? It's change. And Aristotle was the first to say it. It's the kind of chain, or that aspect of change, that enables it to be counted. I'm going to put this in quotes right now. This is a heuristic point of view and not a logically binding conclusion. That was a statement that Einstein made, by the way, in his photoelectric paper when he wasn't very confident of his proposal. And I am not very confident of my proposal in the same way that every scientist on the planet should be if they have a new idea and it hasn't yet been fully validated by experiment. So there's some controversial claims here. I'm basically saying forget the background of time. There is only the time that goes on with change. So when we go to quantum theory, we can start looking at just two atoms. And let's imagine a photon going from one atom to the other. What does the other atom do with it? Well, it can send it right back, and then back again. And so we can end up with a photon clock from Einstein's special relativity paper, which very simply just goes backwards and forwards in time. Now, what's going on here? You can't touch it, because as soon as you touch it, you take energy and information out of it, and you've now, collapsed the wave function. But while it's bouncing backwards and forwards, is time. What's time doing? It gets interesting here. Let's imagine I've got a.
Light do not experience time.
That's proper time based on the Lorentz transform.
So photons move.
Let me describe it very quickly. I'm an atom, and Genevieve here is another atom. I'm going to send her a photon. Of course, it's pointed in her direction, which means that according to the rules of electromagnetism, it's going to do this, or it's going to do this. Now, what do you see as I'm going towards you? It's a clockwise motion, right? Now, I postulate that time is going forward when she receives that. She's received information. She's received energy. Now, she decides to reflect it back to me, and it turns it around, and now I see it going in a clockwise direction, and she sees it going in an anti-clockwise direction. These are Feynman clocks, by the way, straight out of quantum electrodynamics. So the new idea is that time isn't in the space around us. Time is happening along that one-dimensional path between us. So when I let go of this information or energy, time goes backwards for me. When she receives it, time goes forwards for her. But when we swap it around and it comes back in this direction, the opposite happens. So you end up with this hot potato protocol that can occur in perpetuity. It's happening outside of time. I call it subtime. And you can't disturb the system because that would pull it out into decoherence and give you something that would change the system. So the basic idea of subtime, and the paper, by the way, and there's on the website, if you care to look, there's a one-page summary of this, and there's also a paper that was written. I had this idea a long time ago. It tantalized me forever. I finally figured out I can't see what's wrong with it, but I only had a 1% confidence it was right. So I published it in the conference, in a contest last year, and it won 4th prize out of 280 papers. And so I go, oh, other people like it too. And now it's about to be published in a new Springer-Verlag book on the foundations of physics. Now, let me point out something. New ideas in physics have a very high infant mortality. So I am looking for feedback and for critique of this paper. I have put a great deal of thought into it. I think it deserves to be evaluated. But this idea that time is going backwards and forwards along a single path is something I haven't seen anywhere else. Everyone, including Stuckelberg, including Penrose, including Feynman, always talked about a backdrop. They basically built the entire theory on a background of Minkowski space. And what I said is, what if Minkowski space isn't there? What if there's no place I can hang my skyhook? Maybe my skyhook are the two endpoints between the atoms that are coming backwards and forwards. Now, of course, I'm talking about this from a point of view as a photon. It could equally be another boson, particularly one that's a spin one that's massless, for example. Any interaction. Now, the interesting thing that comes up next is, if I'm doing this in a spiral coming to you, it turns out that this whole idea was developed a long time ago in the early days of electromagnetic theory, and pointing, the famous pointing vector fame, actually had this idea of a helical wave in a cylinder traveling between one point and another point. Now, we're used to transverse electric waves and so on. I can answer that question a bit later on, but let me try and get to the point where I can describe where we are. What we're doing is basically saying there is no Minkowski space. Minkowski space is an illusion, just like those planes are an illusion. When you transfer information to someone, there's a certain probability that they will get that object or that information. And that's where the probabilities come in the equations. But what if I use this phrase on you? Everything that can happen can unhappen. And because it's indistinguishable from having happened, time hasn't moved forwards. Now that's interesting because we go underneath the interaction that was going on here with this hot potato photon. What we've got is there's a probability, which is always between 0 and 1, positive, remember, is a probability, that she receives that. But if she sends it back to me, there's now a reverse or an inverse or a negative probability. Now, if you look on the web and look up the whole conversation, there's a whole hornet's nest around this on the concept of negative probability. And Richard Feynman was one of them. So let's take a look at this. What if these helical waves that are going from one photon to another were actually the mechanism that caused interference in a two-phase slit, in a two-slit experiment? And we now have a logical theory that will allow us to construct a wave behavior of light without having to use the apparatus of quantum mechanics to describe pilot waves or whatever else that's going on. Now, this happens to be true for any particle that has a de Broglie wavelength. So what are we looking at? We call this the quantum stroboscope. Along the top, we've got this thing called subtime, which is not really a background, but it's a bigger space of things happening with asynchronous events happening on it. And it's this thing that you're not aware of things going on until you receive something. And then there's long periods of darkness in between. But when you're accounting for your experience, they'll all appear to be tied together in this string of events. Now, if we pull that out and say what's going on in, say, 9 atoms along here, you'll notice that there's a kind of a triangular relationship here. One axis I've called classical time, which is what you think it is, and the other axis is called subtime. So when you can have things bouncing and forwards between atoms, like I just pointed out, for some period of perpetuity, then what happens is you can have two entirely different paths going through this, of this subtime energy or information, but they would appear to be identical in classical time. So in other words, there's a lot of stuff going on under the hood, and in fact, I call this the Nyquist hood. You all know electrical engineers are familiar with the Nyquist theorem. You've got to sample a signal at more than twice the highest frequency that you'd like to extract. Well, what if things are going on so fast under the hood that you've blown it as far as the Nyquist sampling is concerned by maybe an order of magnitude or two? What would you expect? You would expect total randomness, which is exactly what we get when we look at quantum mechanics. Again, I'm telling you this is the theory. It's got a long way to go to be validated. I can look at this in a two-dimensional version of this. But what's really going on is we can look at Bell state measurements and say, okay, we no longer have this thing going on in the background of Minkowski space. We've got something real here. We've got Bob over here, and we've got Alice over here. And when they send each other a photon, it's experienced, with a minus I at this end, which sends it in a clockwise direction, a clockwise direction received by this. And this is experienced clockwise at this end, time going upwards. And then when it sends it back, it gets all reversed. So in other words, time is finite. It's bounded between these two atoms. And if it then goes on to other atoms and then other atoms, then you had an atom altogether, and the total trail becomes your accumulated time, which appears in this thing that we call classical time.
Much like the bracket in Google's database system.
Yes. Speaking of which, there's the thing I told you about before, this assumption of time, and you can have lost and deleted files or duplicate files, because if you're not allowing reversible time in your algorithms, then you won't be able to repair some of the things that go wrong. The reason why two-phase commit it can repair is because it's got this mechanism called rollback, which deliberately allows it to handle a failure. There's the TrueTime API for Google Spanner, and I commend them for that piece of work. It's very well done. But this is really what I'm talking about, something quite different. I'm saying, time isn't this thing that clicks in a big clock in the sky. There's no skyhook you can hang it on. Time is events. It's things that's going on between different pieces of matter. So the conjecture is that subtime is inextricably intertwined with space. And by the way, we all were taught that there is no space without time in special relativity. But if you turn it upside down with an equally true statement, there is no time without space. So in other words, there's a certain implication there that this inextricably intertwined path from one particle to another contains its own information about where it's going. And by the way, this is modular arithmetic. This end and this end can't count the number of revolutions. All they can see is the phase of the final one that lands. And that's what causes reflections and absorptions and so on. This is very interesting because that works very well for two, going backwards and forwards. We now know what the time is between us because we've just created a clock. That's Einstein's photon clock. But what if there was a third person? And here's the interesting issue. We could define simultaneity, or the point we want to agree on time, as it's there with you, or it's here with me, or we might, as a convention, say it's halfway between us. Now, what if we have a third person comes into this game, and we're trying to, A is synchronizing with B, and B is synchronizing with C, therefore C must be synchronized to A. Turns out that's only true if one of them is the source and everyone else is the slave. And that's how our time systems work in this world. All this single source, multiple slaves, gives us this illusion that there's this simultaneity plane, and it's really not. It's an illusion.
I think you're getting confused between natural science and engineering, really.
I'm sure I'm getting confused.
Because I understand why in a computer system you might have some of these concepts, but I don't understand why the natural world insists on sending photons around all the time.
Well, they don't actually send photons around. They send their cousins, they're called packets on networks.
Okay.
And these are the things that create, events that arrive on the network. Packets on networks.
What are these networks?
Any network, it's like Ethernet going onto the wide area network and the internet.
The photons, the light particles bouncing around this room that allow us to see each other.
So everything is a network?
Let me just finish. I want to get through the last slide, and then you can ask questions if that's okay with you. This is a good question. So there's a description here. One of the things I should tell you about is that every theory that comes out, people usually fall in love with because it was their own. A good scientist likes to fail fast. It's like, let me find the hole in my argument. I wasn't able to find the hole in my argument, which is the reason why I published the paper and the reason why I'm here to help people find the hole in the argument for me. So it could easily be criticized as just being one of the other interpretations of the measurement problem. And there's like 5 or 6 different interpretations. The problem is they're all identical when it comes to predicting what the experiments will do. So there's no difference between them. You can't measure the difference. I have described in the paper differences. You can, for example, measure different atomic clocks relative to each other, and this predicts that you will have arbitrary variations going on between any 2 atomic clocks. There is no set of atomic clocks in the world that keeps perfect time with each other. They're all going off, drifting in different directions and affected by, temperature, especially affected by temperature. And so that's why we have to have this committee vote in the world about what time is, because it's the average of all of these. Can you imagine if we had a committee vote to decide what pi was? pi has a science behind it and a magnificent set of mathematics, but time doesn't. I mean, the way we're using it right now in this, we vote on it, and this weighted voting system to say what time should be today, seems to me to be a very shallow foundation for building our systems on. The second thing I said, and this is interesting, because of this quantum stroboscope idea, it basically says that all of the individual atoms are not experiencing all the things that's going on. They're only experiencing what's happening to them. This is a very local observer view perspective, as opposed to a God's eye view perspective. What that means is that there's a massive amount of concurrency available here that you can't see. Now that's interesting because that's reminiscent of the kind of massive parallel concurrency that we're expecting in quantum computing. So one of the predictions is that we might not have all that available parallelism in quantum computing. What we're really doing is multiplexing ourselves on the same hardware and getting the illusion that we're getting that might happen. Now it turns out that a few weeks ago, the largest quantum computer in the world, the D-Wave 512-bit machine, was benchmarked. And it was benchmarked against a standard desktop computer. And they discovered that it was slower than the standard desktop computer in various algorithms. There's a lot of discussion on the internet right now about why this is so and what should happen and how the D-Wave company is explaining this. Now, is this a smoking gun? Possibly, but it's far from conclusive. So the point is, I'm giving you some tools to think about time. If time literally is going backwards and forwards in these ways, then how can we use them differently in solving our problems in computer science? For example, in solving things like security issues and reliability issues. And how can we patch our systems back together quickly after a disaster, when we want to do disaster recovery? These are all the things that I've been thinking about, and I would commend to you to think about differently. So my call to action would be, can we think differently about security? Can we think differently about heartbeats in particular? Why do we have to have these heartbeats in Hadoop that, do strange things? And for example, in the Oracle rack, if you have more than a certain number of nodes in the system, the heartbeat traffic swamps all of the other traffic going on, and so you can't build a cluster any bigger than that. So it turns out that there's reason to re-examine our assumptions regarding time, because I believe that all of these things can be significantly improved by computer science if we were to think about it that way. So thank you. Well, I was here a few years ago giving a talk entitled Rethinking Time in Distributed Systems. And that talk was really all about laying the groundwork for doubt, that the way that we look at time in computer science is a oversimplification. And when we discuss the difference between physicists and computer scientists, I said that both physicists and computer scientists don't understand time, but at least physicists will admit it. What this talk is about is to go quite a bit deeper and actually do the best I can in a lecture of this time, a short introduction to some of the key problems that arise when you start thinking deeply about time, and then try to relate them to what we do in designing our software and architecting our infrastructures. And I hope to just sow at least a seed of doubt in the minds of computer scientists that their existing concept of time needs to be re-examined. So that's my goal for today. I begin with a computer science quote, which I actually love. It's from a book by Andrew Hodges, which talks about Alan Turing, and it's a very famous book amongst our friends here at Stanford. But he pointed out something very interesting, that Church's ideas and Turing's machines are rooted on this concept of doing one thing at a time. But we really don't know what doing is, and we really don't know what time is, until we dive deeper into the mysteries of quantum mechanics and start to understand what we really are getting at the macroscopic measurement of these observations that seem to confound us when we try to think logically about them. So what I'm going to do today in the time allotted is to try to give you an idea, several products that you can buy from companies that claim to do it. It's just that they're not used in OpenSSL. Which goes on to say, well, should we use timestamps differently? Wall Street wants to do high-frequency trading, and there's lots of discussion about using timestamps for various reasons that, as I'll go into later on today, that won't work, at least not the way they think it will. Can we do transactions in a different way? And I hope to be able to sow seeds of doubt here that the common way of doing two-phase commit, for example, in a database, up in the application layer, using this theory called serializability, is actually not a good way to do it, because first of all, it's an extremely low performance way of doing things, and secondly, it also has a much higher likelihood of failing for various reasons because of all the extra code it has to go through. We'll talk about that later. And then the big one here is concurrency. I heard a very famous computer scientist from UC Berkeley talk about SDN recently. I won't mention his name. You can find him on YouTube. Look for UC Berkeley. He also did a great talk at Ericsson too, with a lot of similar material. And he said, there's probably about 10 people in the world who understand concurrency or distributed systems. And I was thinking, what a thing for a computer science professor to say. I'm thinking, wow, doesn't that just be a big red flag that there's something wrong with the discipline of computer science if we don't know how to teach distributed systems and only 10 people in the world know how to do it? And I have myself experienced lots of people working for me in my prior lives who've done lots of distributed systems, and I think the thing that is missing is that those 10 don't even know. And I want to try and convince you, at least a little bit today, that one of the reasons might be that their underlying assumptions of what they're doing is based on a flawed understanding of time. And if that's true, and I think it is, then we might be able to do an idea that will make you walk away and think and say, I want to learn more about that. And then hopefully you'll follow up some of the references that I've given in the end of the paper, and also the end of the presentation. The last page has a bunch of references on. And we might be able to continue the dialogue. I mean, the computer science faculties around the universities around the world to say maybe there is an elephant under the table here that we should be paying attention to. So first of all, I want to point out something. This work is based on the work of many other people. And in particular, I'm not claiming credit for most of what this is. The core ideas go back to Stuckelberg and to Richard Feynman, who actually laid the foundation of what I'm about to tell you today. The talk is going to be in three parts. But before I say that, the key people that I've actually talked to some of these issues about, who have generously shared their time and asked and answered my questions, very often for several hours in their offices in their institutions. And I'm deeply indebted to the questions that they have asked me, and I'm absolutely certain that they will probably disagree with a lot of what I say, and it would be a very lively conversation, as it always is, because each of these experts actually argue amongst themselves a lot more than they argue with me at the moment. I have also targeted this talk to this audience. So if we have computer scientists and electrical engineers and physicists in the room, I hope not to offend the physicists. I hope not to offend the computer scientists, but I hope to, get right to the core of the electrical engineers guys, because you're the ones that's to blame for some of these things, because you should know better. You've done Maxwell's equations after all. So the motivation for me is what I'm doing in my life is I'm making computer infrastructures more reliable and more secure and more agile. Those are the very carefully chosen words that I use with the people I'm working with. And you'll notice that the word security is in there, smack dab in the middle, and it fundamentally is something that we need to do something about security. You know, for example, we think about reliability, but perhaps we need to think about it deliberately in a different way because things keep failing. I mean, all of these Dropbox outages, all the Google Mail outages, all the AWS outages, I mean, they just keep coming up. Every time I see these emails come up, I just store them in like a log of all these things happening. And it's now getting to be hundreds of thousands of reports that these things are offline for periods of time. So it's an interesting question about reliability. And I use that word instead of availability because they tend to do some spin doctoring around the word availability. Can we talk about security differently? Security is absolutely the heart of what I've been working on for probably now 6 years. And it was because 6 years ago, actually 7 years ago, I had an incident working on a government contract out of my house with several other engineers, and I ended up with all my machines being polluted, and I couldn't figure why. And the last thing I wanted to do was to become a security expert. Unfortunately, it didn't help me. I got swamped with, and I had a friend who was the director of network security at Lawrence Livermore Labs, who came to my house and he put a packet sniffer on my wires. And he said, "This is not an ordinary attack. You're under a professional attack." I went, "Oh my God, what's that? I've never heard of it before." And he said, I said, "What should I do about it?" He said, "First turn on your networks." He said, "Then dump all your PCs, buy some Macs, and you might buy yourself some time." So I bought a Macintosh that day, and I actually had it up and running with my QuickBooks accounts on it. I think it took me like 45 minutes, and I was blown away because I spent weeks and months trying to get all these viruses off these machines. That was my wake-up moment for security, and ever since then I've been thinking paranoid thoughts about it. So you know where I'm going on this. Security isn't just about encryption and key management, it's also about presence management. How do we do heartbeats? Why do we do heartbeats the way that we do? And why aren't the heartbeats themselves in a protocol which guarantees that they can't be snooped? And this is actually not a hard problem. I know of several people who claim to have an algorithm that can solve that, and they're far better than we're doing right now in building concurrent systems. By the way, the reason why even the very best can't understand distributed systems is because as soon as you get beyond a certain scale, a certain size of number of machines, the cognitive complexity goes through the roof, and a single human brain can't hold it all. And that's really the reason. But there are other reasons. Even if a single human brain could hold all the information that he was ever told and be able to compute it, thinking through his algorithms, you still find that we don't have a good foundation for the way that our infrastructures work when it comes to time. So I'm going to give you 3 parts to this presentation. Part 1 is basically the physics, and I hope to be able to talk to an audience who's at least heard of special relativity and general relativity before, and may have a passing, acquaintance with quantum mechanics. I can't, in this time available, go deep, unfortunately. I will be very happy to point you to the great places on the web where you can get really good educational material on these. In particular, Stanford has an awesome set of lectures that Lenny Susskind did on general relativity, on special relativity, and also quantum mechanics, which he's very famous for. And I thoroughly commend them to you if you want to learn this stuff. Do beware, if you are Leonard Susskind is how it's spelled. I do beware, physicists and mathematicians and engineers and computer scientists all speak different languages. So their conventions in their mathematical symbols and the way they draw space-time diagrams is all different. So the language barrier is kind of like first understand the different symbology and then understand the different diagrams, and then you can really understand it much easier after that. So I'm going to begin right now with this term, the skyhook. A lot of us in England, I don't know if this happens in the United States too, we're apprentices, helping our fathers and, getting a spare job on the side, outside of school, on building sites, for example. And the site manager would typically, when you first came on the